Hello everyone. In the last lecture, we have discussed about the reactivity of aryl halides towards the nucleophilic substitution reaction. Today, we will start the new topic addition elimination mechanism. Addition elimination mechanism. Now, first of all, what is the addition reaction? What is the addition reaction? The reagent molecules adds to the across the double or triple bond. It's the addition of the reagent across the double or triple bond of an unsaturated molecules. Of an unsaturated molecules, such a reactions is called as a addition reaction. It's addition of the reagent across the double or triple bond of an unsaturated molecules. Such a reaction is called as a addition reaction. And what is the elimination reaction? What is the elimination reaction? In this reaction, the two atoms or group attach to the adjacent carbon atom. In this reaction, two atoms or groups attached to the adjacent carbon atoms are removed without being replaced. This is called as a elimination reaction. This is called as a elimination reaction. Now this type of mechanism is followed by the halonitroarenes. This type of mechanism is followed by the halonitroarenes with the nucleophiles. Halonitroarenes with the nucleophiles like the alkalis, ammonia, amines, etc. The reactions involve two steps. The reactions involves two steps. In step 1, the addition of nucleophile to the aromatic ring. In step 1, the addition of nucleophile to aromatic ring, and in second step, the elimination of halide ions. The elimination of halide ions. Now let's see the step 1, addition of nucleophile to aromatic ring. Addition of nucleophile to aromatic ring. Now this is a para-chloronitrobenzene. This is a para-chloronitrobenzene. The nucleophiles like the hydroxide ions, cyanide, ammonia first adds to the double bonds. First add to the double bond of the aromatic ring. Means addition reaction means the reaction in which the addition of the reagent across the carbon-carbon double bond, across the double bond or triple bond. Okay, such a reactions are called as a addition reaction. Means here the addition of nucleophile across the carbon-carbon double bonds, across the carbon-carbon double bond of the aromatic ring. Okay, this generate the anions when the attack of nucleophile on these carbon atoms. Okay, on carbon atom, then that time the negative charge is present on the ortho position, ortho carbon atoms. The generate the anions with the negative charge on the aromatic ring. Okay, when the nucleophile hydroxide ions is attached on the carbon atom, then that time the bond is a break on the direction of the ortho carbon atom. Then the negative charge is present on the ortho carbon atoms. This generates the anion with the negative charge on the aromatic ring. Normally, such aromatic anions are unstable. Normally, such aromatic anions are the unstable. However, the strong electron withdrawing group, like the nitro group helps to stabilize the negative charge. This nitro group is attached to the para position to the chlorine atoms. Okay, this nitro group is which is a para to the chlorine atom. So this is a electron withdrawing group, and this electron withdrawing group has stabilized the negative charge by the resonance. Stabilize the negative charge by resonance. This lowers the activation energy of the step. This electron withdrawing group lowers the activation energy of the step and makes the reaction is possible. This is a slow step. Hence this is called as a rate determining step. This is a slow step, and hence it is a rate determining step. Now the example is given here, the para-nitrochlorobenzene. When the nucleophile is attached on the carbon atom, then the bond between the carbon-carbon double bond is break on the direction of the carbon orthocarbon atom. This orthocarbon carries a partial negative charge. Again, this negative charge is a delocalized here the benzene ring, and then this bond is break on this para carbon atom. This para carbon carries a partial negative charge. Again, the nitro group is attached to the para position. This negative charge is stabilized by the nitro group here. Again, this negative charge is stabilized here the formation of the double bond, and this bond is break on this oxygen atom. This is a second resonance structure. Again, the negative charge is present on this oxygen atom. Again, this negative charge is stabilized here, delocalized here. Again, this bond is between the carbon and nitrogen can break here in these directions. Again, the bond is break orthocarbon. The negative charge is present on the orthocarbon atoms here, like that. Okay, and in the last step, in the last structure, the chlorine atom or group is a displaced here. The negative charge is a shift here, again delocalized here, and then this bond is break in the directions. Okay, the first step is a slow step. Okay, the first step is a slow step, and second step is a fast step. This in the rate determining step, the nucleophile is attached on the carbon atom. Okay, the bond is break in the direction on this orthocarbon atom. The orthocarbon carries a negative charge. This negative charge is stabilized by the electron withdrawing group, which is attached to the aromatic rings. This nitro group has the lowers the energy of activation and makes the reaction is possible. And this is a slow step, and hence this is called as a rate determining step. Now in step number 2, the benzene ring cannot accommodate the negative charge. The benzene ring cannot accommodate the negative charge. Hence, the halide ions is lost. In second step, the benzene ring. In second step, the benzene ring cannot accommodate the negative charge. Cannot accommodate the negative charge. The halide ions here the loss here. Halide ion is a loss here. Therefore, the removing the negative charge on the ring, and there the removing the negative charge on the ring. This is in the first step. This is in the second step. As both substrate and nucleophiles are involved in a substrate means reactant and nucleophile both are involved in the rate determining step. Both are the involved in the rate determining step or slow step. Such a reactions is called as a second order nucleophilic substitution aromatic reaction, because they are the substrate and the nucleophiles which are the involved in the rate determining step, Such a reactions are called as a second order nucleophilic substitution aromatic reaction. Such a reactions are called as a second order nucleophilic substitution aromatic reaction. Now the energy profile diagram, the energy profile diagram shows that the first step has a high energy of activation. The first step is a high energy of activation. The energy profile diagram shows that the first step that means a slow, the addition of nucleophile to the aromatic ring. The addition of nucleophile to the aromatic ring has a high energy of activation, high energy of activation, and it is a slow step. Okay, it is a slow step. Whereas in the second step, when the elimination of halide ions, in second step, this is a fast reaction, fast step. Okay, and then the energy of activation is very low. The energy of activation is very low. Okay, that means in this energy profile diagram, the potential energy against the reaction coordinate. Okay, in the first step, the high energy of activation, that means it is a slow step, and the second step is the fast reaction, and it has the low energy of activation. It has a low energy of activation. Now, similarly, amine reacts with the amine here, the nucleophile, okay, methyl amine reacts with the para nitrochlorobenzene. Methyl amine is a reacts with the para nitrochlorobenzene with the same types of the mechanism. When same types of the mechanism. Here the lone pair is present on the nitrogen. It is a this amine is a methyl amine is a electron rich. Okay, and this attacks on the carbon atom. This attacks on this carbon atom. Then that time the bond between the carbon double bond is a break on this direction. On this direction, this orthocarbon carries a partial negative charge. The CH3NH2 is a attached to this carbon atom. Okay, this chlorine containing this carbon atom. This bond is break in this direction. The orthocarbon carries a negative charge. Again, this negative charge is a delocalized in this benzene ring. This negative charge is a delocalized in this benzene ring. So the again this bond is a break on this para carbon. Okay, this bond is break on the direction of the para carbon. This para carbon carries a, again partial negative charge. The para carbon carries a partial negative charge. Hence, here the nitro group is an electron withdrawing group is attached to that of the para position, and then this nitro group is an electron withdrawing group, and then this negative charge again here the delocalized in the nitro group. Okay, in this nitro group, then the oxygen carries a, here the oxygen carries a negative charge again. In the next step, in the next resonance structure, the negative charge again delocalized here. Then the bond between the carbon and nitrogen again break in the direction on this carbon-carbon single bonds. Okay, here formation of the double bond. Okay, here the formation of double bond, and again this double bond is break on this ortho direction here. This ortho carbon carries again the negative charge. Okay, again in the next step, what happen? This negative charge is a delocalized here and then the halogen atom is a displaced here the halogen atom is a displaced here, then to form the yeah a double bond again, and then CH3NH is attached here at the position of the chlorine atoms. Okay, at the position of the chlorine atom. The first step is a slow step, second step is a fast step. Okay, now today we stop here. Thank you.